The fourth example of thinking with the work-kinetic energy theorem is in this example scenario of circular motion. So circular motion, what means to be a circle is the thing is moving such that its trajectory stays the same distance, say radius capital R, so R is a constant, some sort of a distance. But this R is always constant. So this is what circular motion means. Uniform circular motion doesn't really have to do with that R. It has to do with the fact that if you are in uniform circular motion, this little object is moving with a constant speed, right? So the magnitude of the velocity vector is always the same value. The velocity vector, though, it may have a constant magnitude, but it is definitely not constant. And the reason is because when the little ball is over here, it has this velocity, but when it's on the diametrically opposite side, for example, it's actually got precisely the opposite velocity, because it's got the same speed, but it is in exactly the opposite direction, right? So I could study this as an initial final situation in the language of the work-energy theorem, for example. Yeah, so anywhere you check, the velocity is precisely tangential to the trajectory curve. The trajectory curve is this circle, and the velocity is tangential to it. Okay, so in particular, the velocity is not constant, the vector is not constant, because the direction is always changing, but the magnitude of the velocity vector is constant. The speed is always the same for uniform circular motion. All right, so the reason why this object can go in a circle, so in particular for uniform circular motion has some very careful rules. In particular, that the net force on, let's say this little object has mass m, so the net force on m is purely centripetal. So that is, there are no other forces on the object M that are non-centripetal, is the idea. But so I've got this idea. So the net force on M is the centripetal force, and if you remember when you learned about the centripetal acceleration, and then Newton's second law applied to the centripetal acceleration problem gives rise to this centripetal force idea. Centripetal means center pointed. So the centripetal force on the object when it is here is center pointed. And when the object is over here, the centripetal force is this way. And if the object is here instead, the centripetal force is this way. It always points towards the center. It's called the center-pointed force, the centripetal force. So what's interesting about that is to ask, what is the work done by the centripetal force? So in uniform circular motion, we know that the work done by the centripetal force is always going to be zero. It's always zero because the kinetic energy does not change. There is no work done by the center-pointed force. There is another way to understand this, actually. It's to look at what is the work done by the centripetal force if we ask in small amounts. So this is the calculus infinitesimal d. It's equal to the centripetal force vector dotted with a small displacement, ds, right? So this is a small amount of work done. And secretly, if you go, let me do it kind of softly in red. If I add up, I will get all of the work done by the centripetal force. So that's adding it all up. And this will always add, no matter where you put initial and final, it will always add to 0. That's always going to be the answer in this uniform circular motion case, because the kinetic energy never changes, right? The kinetic energy, no matter what's I, what's F, kinetic energy never changes. But I don't really want to study it from this point of view. Let's study this. So at this place right here, the velocity is this way, and the force is center pointed. The velocity is tangential and the force is center pointed. So the center pointed force vector is this one. And if I dot with, check this out, this is ds, but I'm going to rewrite it. This is center pointed force dotted with the velocity times dt. So you know that dx by dt is v, right? This is a generic kind of statement about the relationship between the velocity and the time rate of change of the location or position. So if I multiply both sides, I can say that there is a small displacement because for a small amount of time, I traveled with that velocity v. This can be written as a vector as well, right? D by dt of the location vector is the velocity vector. So all I've done is I've taken this displacement vector and replaced it by velocity times dt, a small amount of time. And if I look at this thing right here, the center pointed velocity is this way, the velocity is always tangential, so this is always at right angles. And the dot product is always going to be 0 for perpendicular, right? Perpendicular vectors, because the so this always is going to be 0. You're always going to take the cosine of 90 degrees, that 90 degrees. Over here it's 90 degrees, over here it's 90 degrees. This is a big deal. Forces perpendicular to motion do not do work. Or actually, how about cannot? They are not allowed. They just don't. And the reason is because you're always going to have this cosine of 90 in the dot product, because 90 is what perpendicular means. So let me enhance this example just a little bit. Remember, we're not out to calculate anything really. We're more out to just explore with the Work-Kinetic Energy Theorem. I'm alluding to calculations, like the dot product in a perpendicular case. It's always just going to be 0. Yeah. So let me go here. Check this out. Let me put something in circular motion. It's kind of in circular motion. And it's uniform circular motion, but if you listen really carefully, do you see that this thing going in a circle, like I'm causing it to do? I have to continually use a force to drive it, because it's rubbing on the table. There's friction. And you can imagine that if you set up a scenario where you have a string and an object, and it's on a table, right? As you swing, like as you tug on this string, so you're just like going like this with the string to get the object to swirl around on the table, it's going to be sliding. And the idea is you have to tug on the string just right to maintain uniform circular motion. You have to actually tug on the string a little bit in a kind of an interesting way. And the reason you have to tug on the string is you are not allowed just to use a center-pointed force. You have to actually pull on the object in its direction of motion a little bit. So what I mean by that is, let me draw. So here's the object. The motion it's doing, I'm going to exaggerate it a bit. Let's see if I can exaggerate it correctly. The motion it's doing is probably going to do it wrong on my first drawing here. But can you see that the string is, oh, it's kind of like I'm applying a pulling force. So this is like a force by a person, or a pull, and it is off the center of my circular path. This is the center of the circle, and this is where the end of the string is. And the idea is this pull force, this force is, so this force, let me go down and draw it. So I've blown it up to look a little bigger. This pull force is doing two different things. It's a combination of what is required as the centripetal force plus, right, this force vector is plus this vector. This is the force that fights friction. And where this center-pointed force can never do work, the work for F centripetal is always going to be 0. This force, though, is going to be able to do work. This force does positive work. Yeah, so this force is the reason why you can continue, even while this thing is sliding on a rough table with friction. This component of the pulling force is responsible for fighting the friction, while the other component that makes up this pulling force, this component is purely to cause the object to maintain its circular motion. Yeah, so that the net force is this is a centripetal force. Yeah,